In statistics, the bias of an estimator is the difference between this estimator's expected value and the true value of the parameter being estimated. An estimator or decision rule with zero bias is called unbiased. Otherwise, the estimator is said to be biased. In statistics, bias is an objective statement about a function, and while not a desired property, it is not pejorative. Unlike the ordinary English use of the term bias, bias can also be measured with respect to the median, rather than the mean, in which case one distinguishes median unbiased from the usual mean unbiasedness property. Bias is related to consistency in that consistent estimators are convergent and asymptotically unbiased, though individual estimators in a consistent sequence may be biased. See bias versus consistency. All else equal, an unbiased estimator is preferable to a biased estimator, but in practice all else is not equal. Unbiased estimators are frequently used, generally with small bias. When a biased estimator is used, the bias is also estimated. A biased estimator may be used for various reasons. Because an unbiased estimator does not exist without further assumptions about a population or is difficult to compute, because an estimator is median unbiased but not mean unbiased, because a biased estimator reduces some loss function compared with unbiased estimators, or because in some cases being unbiased is too strong a condition, and the only unbiased estimators are not useful. Further, mean unbiasedness is not preserved under nonlinear transformations, though median unbiasedness is. For example, the sample variance is an unbiased estimator for the population variance, but its square root, the sample standard deviation, is a biased estimator for the population standard deviation. These are all illustrated below. Definition. Suppose we have a statistical model, parameterized by a real number theta, giving rise to a probability distribution for observed data, and a statistic which serves as an estimator of theta based on any observed data. That is, we assume that our data follows some unknown distribution, and then we construct some estimator that maps observed data to values that we hope are close to theta. Then the bias of this estimator is defined to be where denotes expected value over the distribution, i.e., averaging over all possible observations. The second equation follows since theta is measurable with respect to the conditional distribution. An estimator is said to be unbiased if its bias is equal to 0 for all values of parameter theta. In a simulation experiment concerning the properties of an estimator, the bias of the estimator may be assessed using the mean sign difference. Examples. Sample variance. The sample variance of a random variable demonstrates two aspects of estimator bias. Firstly, the naive estimator is biased, which can be corrected by a scale factor. Second, the unbiased estimator is not optimal in terms of mean squared error, which can be minimized by using a different scale factor, resulting in a biased estimator with lower MSE than the unbiased estimator. Concretely, the naive estimator sums the squared deviations and divides by n, which is biased. Dividing instead by n-1 yields an unbiased estimator. Conversely, MSE can be minimized by dividing by a different number, but this results in a biased estimator. This number is always larger than n-1, so this is known as a shrinkage estimator. As it shrinks the unbiased estimator towards 0, for the normal distribution, the optimal value is n+1. Suppose x1, xn are independent and identically distributed random variables with expectation mu and variance sigma 2. If the sample mean and uncorrected sample variance are defined as, then S2 is a biased estimator of sigma 2, because in other words, the expected value of the uncorrected sample variance does not equal the population variance sigma 2, unless multiplied by a normalization factor. The sample mean, on the other hand, is an unbiased estimator of the population mean mu. The reason that S2 is biased stems from the fact that the sample mean is an ordinary least squares estimator for mu is the number that makes the sum as small as possible. That is, when any other number is plugged into this sum, the sum can only increase. In particular, the choice gives. And then note that the usual definition of sample variance is, and this is an unbiased estimator of the population variance. This can be seen by noting the following formula, which follows from the B-An formula. For the term in the inequality for the expectation of the uncorrected sample variance above, the ratio between the biased and unbiased estimates of the variance is known as Bessel's correction. Estimating a Poisson probability, a far more extreme case of a biased estimator being better than any unbiased estimator, arises from the Poisson distribution. Suppose that X has a Poisson distribution with expectation lambda. Suppose it is desired to estimate with a sample of size 1. Since the expectation of an unbiased estimate of delta is equal to the estimand, i.e., the only function of the data constituting an unbiased estimator is to see this. Note that when decomposing E minus lambda from the above expression for expectation, the sum that is left is a Taylor series expansion of E minus lambda as well, yielding E minus lambda equals E minus 2 lambda. If the observed value of X is 100, then the estimate is 1, although the true value of the quantity being estimated is very likely to be near 0, which is the opposite extreme. And, if X is observed to be 101, then the estimate is even more absurd. It is -1, although the quantity being estimated must be positive. The maximum likelihood estimator is far better than this unbiased estimator. Not only is its value always positive, but it is also more accurate in the sense that its mean squared error is smaller. Compare the unbiased estimators MSE of the MSEs of functions of the true value lambda. The bias of the maximum likelihood estimator is maximum of a discrete uniform distribution. The bias of maximum likelihood estimators can be substantial. Consider a case where n tickets numbered from 1 through to n are placed in a box and 1 is selected at random, giving a value x. If n is unknown, then the maximum likelihood estimator of n is x. Even though the expectation of x is only 2, we can be certain only that n is at least x and is probably more. In this case, the natural unbiased estimator is 2x minus 1. Median unbiased estimators. The theory of median unbiased estimators was revived by George W. Brown in 1947. An estimate of a one-dimensional parameter theta will be said to be median unbiased if, for fixed theta, the median of the distribution of the estimate is at the value theta, i.e., the estimate underestimates just as often as it overestimates. This requirement seems for most purposes to accomplish as much as the mean unbiased requirement, and has the additional property that it is invariant under one-to-one transformation. Further properties of median unbiased estimators have been noted by Lehman, Birnbaum, van der Vaart and Fanzel. In particular, median unbiased estimators exist in cases where mean unbiased and maximum likelihood estimators do not exist. Besides being invariant under one-to-one transformations, median unbiased estimators have surprising robustness. Unfortunately, there is no analog of Rao-Blackwell theorem for median unbiased estimation bias with respect to other loss functions. Any minimum variance mean unbiased estimator minimizes the risk with respect to the squared error loss function, as observed by Gauss. A minimum average absolute deviation median unbiased estimator minimizes the risk with respect to the absolute loss function, as observed by Laplace. Other loss functions are used in statistical theory, particularly in robust statistics. Connections between loss functions and unbiased estimation were studied in many works. Detailed description of corresponding results is given in Chapter 3 of the book Robust and Non-Robust Models in Statistics by Lev B. Klebanov, Svetlos R.T., Ratchev and Frank J. Fabozzi, Nova Scientific Publishers, Inc., New York, 2009. Effective transformations. Note that, when a transformation is applied to a mean unbiased estimator, the result need not be a mean unbiased estimator of its corresponding population statistic. By Jensen's inequality, a convex function as transformation will introduce positive bias, while a concave function will introduce negative bias. And a function of mixed convexity may introduce bias in either direction, depending on the specific function and distribution. That is, for a nonlinear function f and a mean unbiased estimator u of a parameter p, the composite estimator f need not be a mean unbiased estimator of f. For example, the square root of the unbiased estimator of the population variance is not a mean unbiased estimator of the population standard deviation. The square root of the unbiased sample variance, the corrected sample standard deviation, is biased. The bias depends both on the sampling distribution of the estimator and on the transform, and can be quite involved to calculate. See unbiased estimation of standard deviation for a discussion in this case. Bias, variance and mean squared error. While bias quantifies the average difference to be expected between an estimator and an underlying parameter, an estimator based on a finite sample can additionally be expected to differ from the parameter due to the randomness in the sample. One measure which is used to try to reflect both types of difference is the mean square error. This can be shown to be equal to the square of the bias plus the variance. When the parameter is a vector, an analogous decomposition applies. Where is the trace of the covariance matrix of the estimator? An estimator that minimizes the bias will not necessarily minimize the mean square error. Example: estimation of population variance. For example, suppose an estimator of the form is sought for the population variance is above, but this time to minimize the MSE. If the variables x1, xn follow a normal distribution, then ns2, sigma 2 has a chi-squared distribution with n-1 degrees of freedom, giving. And so with a little algebra it can be confirmed that it is C equals 1, which minimizes this combined loss function, rather than C equals 1, which minimizes just the bias term. More generally, it is only in restricted classes of problems that there will be an estimator that minimizes the MSE independently of the parameter values. However, it is very common that there may be perceived to be a bias-variance trade-off, such that a small increase in bias can be traded for a larger decrease in variance, resulting in a more desirable estimator overall. Bayesian view. Most Bayesians are rather unconcerned about unbiasedness of their estimates. For example, Gelman et al. Write, from a Bayesian perspective, the principle of unbiasedness is reasonable in the limit of large samples, but otherwise it is potentially misleading. Fundamentally, the difference between the Bayesian approach and the sampling theory approach above is that in the sampling theory approach the parameter is taken as fixed, and then probability distributions of a statistic are considered, based on the predicted sampling distribution of the data. For a Bayesian, however, it is the data which is known, and fixed, and it is the unknown parameter for which an attempt is made to construct a probability distribution, using Bayes' theorem. Here the second term, the likelihood of the data given the unknown parameter value theta, depends just on the data obtained and the modeling of the data generation process. However, a Bayesian calculation also includes the first term, the prior probability for theta, which takes account of everything the analyst may know or suspect about theta before the data comes in. This information plays no part in the sampling theory approach. Indeed, any attempt to include it would be considered bias away from what was pointed to purely by the data. To the extent that Bayesian calculations include prior information, it is therefore essentially inevitable that their results will not be unbiased in sampling theory terms. But the results of a Bayesian approach can differ from the sampling theory approach even if the Bayesian tries to adopt an uninformative prior. For example, consider again the estimation of an unknown population variance sigma 2 of a normal distribution with unknown mean, where it is desired to optimize C in the expected loss function. A standard choice of an informative prior for this problem is the Jeffreys prior, which is equivalent to adopting a rescaling invariant flat prior for lane. One consequence of adopting this prior is that S2, sigma 2 remains a pivotal quantity, i.e., the probability distribution of S2, sigma 2 depends only on S2, sigma 2, independent of the value of S2 or sigma 2. However, whilst in contrast, when the expectation is taken over the probability distribution of sigma 2 given S2, as it is in the Bayesian case, rather than S2 given sigma 2, one can no longer take sigma 4 as a constant and factor it out. The consequence of this is that, compared to the sampling theory calculation, the Bayesian calculation puts more weight on larger values of sigma 2, properly taking into account that under this squared loss function the consequence of underestimating large values of sigma 2 is more costly in squared loss terms than that of overestimating small values of sigma 2. The worked-out Bayesian calculation gives a scaled inverse chi-squared distribution with n-1 degrees of freedom for the posterior probability distribution of sigma 2. The expected loss is minimized when CNS2 equals less than sigma 2 greater than. This occurs when C equals 1, even with an uninformative prior. Therefore, a Bayesian calculation may not give the same expected loss minimizing result as the corresponding sampling theory calculation.